All right, guys, we're back. Our next unit is kind of a few units kind of all lumped together. So we're kind of take it in pieces. And it's all about a lot of mathematical relationships that we can use within chemistry, okay? So this first chunk that we're going to talk about is moles and percent composition, empirical molecular formulas, okay? This is going to be a pretty quick unit, but it's going to help us kind of solidify our mole relationships and solidify our understanding of our formulas, okay? So if we go ahead and flip to the next page if I can. There we go, right? So before we can really understand what's happening, right, we got to understand, again, what we actually did with our baby stoich before, okay? So this is going to be hopefully a little bit of a review for us, right? So if we look at our periodic table, right, what units do we see on the masses, right? If we look down, if we remember on our periodic table, at the bottom of each square, we have the atomic mass, right? So the units on our masses are atomic mass units. Okay? And we can abbreviate that as AMU. So the mass of one oxygen atom would be 16 AMU. So why don't we use grams, right? Normally when we talk about measuring things, we talk about measuring grams. Well, atoms are really super small. It would be very awkward, right? So if we had a mass of oxygen, right, one atom of oxygen, 2.7 times 10 to the minus 23rd grams. That's real awkward, right? So much easier is just to use our AMUs, okay? So first off, we can kind of go through this. You guys should be able to go through it, but a couple of quick ones, right? I know hydrogen is going to be 1 AMU. You can find the others by looking at our periodic table. Hopefully, right, we remember that it's down at the bottom of our squares, okay? So let's then talk about two different types of elements, our monoatomic and our diatomic elements. Okay, so monoatomic elements, right, one atom of an element, stable enough to stand on its own. Really pretty rare, okay? But oftentimes our elements, we can say that it's just one atom of that, or one atom of the element. But we have 7 diatomic elements, okay? So remember that we use the 7 up. We start at element 7, which would be nitrogen. We make a 7, nitrogen, oxygen, fluorine, and then we go down our periodic table, chlorine, bromine, iodine. So that's our 7, and then we got to go up, and that's hydrogen, okay? Astatine, we're going to not worry about you, okay? These elements are always, when they're by themselves, they're always going to be diatomic, okay? So if we have one molecule of oxygen, right, we would have O2, okay? So O2 tells me that I have 2 atoms together. So I would have 2 times 16, which is going to be 32 AMU for my O2, all right? We can flip to the next page here. So what we have is we've got our formula mass and the gram formula mass. Really, these are kind of interchangeable, and most often we use our grams, okay? But our formula mass is the mass of an atom, molecule, or compound in atomic mass units, right? So the formula mass of a hydrogen atom is going to be 2 times 1 AMU, because hydrogen is diatomic, so it's going to be H2. Oh wait, this says hydrogen atom. I was wrong. So it's going to be formula mass of a hydrogen atom is going to be 1 AMU, right? If it was a hydrogen molecule, then it would be H2, and then it would be twice as much. Sorry about that. But our gram formula mass is the mass of 1 mole of an atom, right? We've talked about moles really briefly, but a mole is 6.02 times 10 to the 23rd units of a substance, right? It's like a dozen. So what is really convenient about this number is that 1 mole of carbon is 6.02 times 10 to the 23rd atoms of carbon, but that is 12 grams of carbon. So if we had 12 grams of carbon, right, we're going to have 1 mole of carbon, but 12 is also what we have on our periodic table, right? If we look at our periodic table, the atomic mass on carbon is 12.01. So 12.01 grams of carbon is 1 mole of carbon. That's why this is a really conveniently chosen number, okay? So the gram formula mass of hydrogen, right, is going to be 1 gram, okay? So if we come down here, right, let's do some practice with this, right? Formula mass of K2CO3. Well, potassium is 39. We're going to multiply that by 2. We're going to add carbon, which is 12. We've only got 1 of those. And then we're going to add oxygen, so we're going to do 3 times 16. And when we do that, that would be 138 AMU, okay? But if I come down here to this second question, right, now I'm asked for the gram formula mass, okay? So we're going to calculate the gram formula mass of this copper sulfate pentahydrate. So this is an ionic compound that actually just has some water trapped in it, okay? We're going to talk about these a little bit later in this unit, okay? But we can kind of just take this as it is and calculate our gram formula mass. So I have 1 copper, that would be 63.5. We have 1 sulfur, that would be 32.1. We have 4 oxygen, so I'm going to do 4 times 16. And then we have 5 water molecules, so I got to do 5 times 2 times 1. So I'm going to do 5 times 2 times 1. This is my hydrogen here, plus oxygen is 16. And I'll multiply 5 times that whole thing. So when I do that, my gram formula mass for this whole big weird compound that we haven't really learned about, but we are going to learn about it, the gram formula mass is 249.6 grams per mole of my copper sulfate pentahydrate. Whoops, times, I started saying penta and I wrote 5. There we go. All right, so times 5H2O. So what we should be able to do is to calculate our formula masses, okay? Once we then can do that, then we can just calculate percentages. So if we remember, right, percentages are always going to be the part divided by a whole times 100, okay? But we can calculate percentages by mass, or percent by, in our grams, of each of our pieces. So for example, right, I can see the gram formula mass for calcium chloride, and I'm going to calculate the percentages. Calcium, 1 times 40 is going to be 40.08. That's my part that is calcium. And then 2 times 35.435, 2 chlorines, that's going to be 70.906. So my whole is 110.986, okay? So what we can do is we can do our percent by mass for each of our different elements, okay? So we can say, well, calcium was 40.08, it's the part, divided by the whole, which would be 110.986, multiply that by 100, and we get 36.1% that came from calcium. And then let's do the same thing for chlorine, 70.906 906 divided by 110.986 times 100, and that's going to be 63.9%. That is chlorine. Okay? So we should be able to do each of these practice questions. Okay?